Okay, good morning all. So let's continue where we left off in the previous class. We were kind of quickly rushing through towards the end of the previous class. So today we'll try to maybe quickly review that at a slower pace maybe. So the topic that we were talking about was how to use Laplace transform. So let's quickly review what we have done last time. So what was the definition? So it's Laplace transform of some function of time is nothing but 0 to infinity e to the power of minus st multiplied by that function of time into dt. So this is a like a mathematical tool, just a function like this, and then usually the short form of notation is like this. So instead of writing all this, I just want to write f of s. So these two are same. So having defined a particular Laplace transform like this, then we looked at some example functions. So what were the example functions? So one we looked at was a constant. Okay, so if there is a constant f of t equal to, so maybe I'll just quickly make the table here. So f of t and then Laplace of f of t, or why not use capital F of s. So this will transform to this after applying Laplace transform. So if it was 1, it was 1 by s. So this we have seen last time. Substitute here 1 and then calculate this integration, you will get 1 by s. Okay, I don't want to repeat it again. You can actually, maybe I can quickly do that. If you substitute 1, it is just think of this as 1. So this is minus 1 by s e to the power of minus st, and the limits are 0 to infinity. So when you substitute infinity, it becomes 0, provided s is greater than 0, and then when you substitute 0, it will become e to the power of 0 is 1, but then there will be a minus sign, so minus sign will cancel and then you will get only 1 by s. So like that. Okay, one new function we'll try to see today. What if f of t equal to t itself? Okay, that means what? So if it is a t versus f of t, so it's a line which is 45 degrees like this. Okay, so after 1 second it is 1 volt, 2 seconds 2 volts, 3 seconds 3 volts, like that. Okay. So for that, what is the Laplace transform? This we did not do last class, so let's do it now. So what is that? Just by definition, so I don't write anything here, I'll just t dt. So this is our standard definition of Laplace transform. Okay, so how do you do it now? So we can quickly apply the UV rule just to find out what it is. So let's take u dash equal to e to the power of minus st, and then v equal to t. Okay, so if u dash is this one, what is u? Minus 1 by s e to the power of minus st, and if v is t, then v dash is 1. Okay, so this is just, I am doing this because I want to use that multiplication rule of this one. So what is integration u dash v? Is nothing but uv minus integration uv dash. Okay, so this if I apply for the given function, we'll be able to solve it. So what is that? So I am writing let's say Laplace transform of t. Okay, so f of t equal to t itself. So just a notation. So u into v, that means this into this. So minus t by s e to the power of minus st, and then the limits are 0 to infinity. This is this term minus then now this term, okay, u into v dash. So 0 to infinity minus 1 by s e to the power of minus st into 1, okay, into dt. So this one, if you notice, if I substitute infinity, it becomes e to the power of minus infinity, so this is 0. And then if I substitute 0, then because t is there, this also is 0. So this whole term is equal to 0. We are only left out with this. I can cancel minus. Okay. I can bring 1 by s outside. Okay. So I'll have 1 by s integration 0 to infinity e to the power of minus st dt. Okay. So this will be equal to 1 by s into 1 by s with minus e to the power of minus st 0 to infinity. Okay. Now when I substitute infinity, e to the power of minus infinity is 0. When I substitute 0, it will be 1, but then there will be a minus sign. That minus, this minus will cancel. Finally I am left out with 1 by s square. Okay. So s into s is s square. Okay. So the answer of Laplace transform of t is 1 by s square. Okay. I am just doing it so that later on we will do one problem which has this term. Okay. Now I have one t square, t cube and all the things also we can do, but we will not go into that. You can always find what is the values in, either you can solve it yourself or you can find it in some book. Last time we also saw what is e to the power of at. So f of t is e to the power of at, then a transformation will be 1 by s minus a. Okay. Okay. So so this also we don't require now. Let me quickly review the circuits part also. So maybe I'll write it here. If you have a resistance, okay, and then V is plus minus and then I. So I of t, V of t. Okay. So this is in time domain. Okay. So and Ohm's law is just a multiplication of I of t into R equal to V of t. So this is like V of s equal to I of s into R. So there is nothing interesting there, just multiplication. So if you have inductor, then what happens? So the relation I of t and V of t, so this is the voltage I am applying, therefore some current is flowing, okay, or this is the current I am applying, so some voltage is appearing. So you can interpret it in both ways. So what is the relation here? V of t equal to L into di by dt, or I will write it I dash t. Okay. So this is the, okay. So this is the relation between these two, and when you transform this one, what you will get? So V of t will become V of s equal to, and L will remain L because it's a constant. Now I dash t, Laplace transform of I dash t. So maybe we last time we saw. So if I have f dash of t, then the Laplace transform will be, yeah, s into f of s minus f0. Okay, so this was our last time what we saw. So you can, again I don't want to repeat it. So the same thing I'll use here. So I'll get L into SL into I of s minus, the L will also multiply, L into I of 0, initial current and all. Now you can rearrange this and then write it like this. V of s, this term can come this side, L into I of 0 whole divided by SL equal to I of s. Okay, so just I am rearranging. So and I can further rearrange. So I can This SL I can split it into two terms. So here I can do 1 by SL, and then here that L will cancel, and then by S will come. Okay. Now, if I look at this one, this is in terms of volts. Left hand side is voltage, right hand side is also voltage. This one, right hand side is amperes, current, and this side also is current. Okay. So I can view it in two different ways. Okay. So let's draw this quickly circuit of this. So what happens is here. So this term, this is the impedance and this is the current. Okay. So the current is I of S. The current is I of S, and the impedance is S into L. Okay. So current into impedance will be some voltage here. Okay. But because if there was already some initial current, that will also have consume some voltage. So to represent that, I will have to introduce a voltage source, and this side is plus, this side is minus, because this is minus, it is subtracting from the overall Vs. Okay. So what happens now, this will be L into I of 0, and this voltage I will call it plus minus V of S. Okay. So this total voltage is this voltage minus this voltage. So like that way you have to interpret this. I hope it is correct with the signs, plus minus. Is it correct? Yeah, looks like it is correct. Anyway, now this is coming because of this equation. Okay, but you can also look at this equation. You can draw another kind of circuit. Okay, so what is that? So the current Is is there. The current Is is flowing. So this is known, and the current I am sending it. It will divide into two different paths. So one path is like this, other path is like this. So I can show two different paths like this. So this one will be a current source. I'll put the arrow like this, and the magnitude will be I of 0 by S, and the other will be impedance into voltage. Sorry, voltage divided by impedance. Okay, V by impedance. So this will be this, anyway, the impedance itself is SL, and this voltage will be V of S, like this. Okay. So this total current is divided into two paths. So these two terms. So you can interpret it like this. Okay. So all these problems come only if there are some initial conditions. That means initially some current is flowing, or initially some current is flowing here. So if that is not there, then I can always short circuit this, and it becomes very straightforward kind of thing. Now one thing you should notice, on the left side is a differential equation. This is a differential equation because of the differentiation. On the right side, it's an algebraic equation. So the application of Laplace transform, converting a differential equation into a algebraic equation, so that you can manipulate easily. It's like algebraic calculation. So we'll see one example on that also. So maybe quickly now I go to capacitor. The capacitor is like this, I of t and then V of t. So the relation is, let's say I of t equal to C V dash t. Okay. So this is one way of writing it, or you can also write V of t is 1 by C integration of I of t. Okay. Now when you apply Laplace transform, the same thing happens. So let's just quickly simply instead of rewriting everything, maybe I'll directly write, or it's just the same thing with just change of variables. So I'll write I of S equal to C into, what is the Laplace transform of this? S into V of S minus V of 0. So I can write C, okay, Cs into V of S minus C into V of 0. Okay, so this is I of S. So this I can write it, current is flowing I of S, divides into two parts, but then this part minus sign is there, so maybe I'll use it, show the direction like this, and then this one is CV of 0, and the direction is like this, and this direction is like this. The remaining current flows here, and then the impedance of this. So see, I should write it, if I want to write amperes equal to volts divided by ohms. Okay, so this CS is already there like this, so I can always put 1 by CS, and then I can remove this. So this is equivalent. So this part is having a unit of ohms. Okay, so I can use 1 by CS here. Okay. So moral of the story is, whenever you see impedance like inductance, you can, the impedance is SL, and then whenever you see this one, it is 1 by CS. And the other way to interpret it is, you can always write, you can write it in terms of Vs. So C will come here. Maybe I'll use this place only. So Is by C equal to, and then plus V of 0. Okay, so is equal to V of S. That S I will bring it this side, so it will be like this. Okay. So the total voltage divided into two parts. One part is this voltage and the other part is this voltage. So you can always, here also it was like this, so plus minus V of S. So the same thing. So I can show like this. The sign we have to see now. So yeah, it is like this: high voltage, low voltage, high voltage, low voltage, and then, so this plus this is nothing but this. So V of S. So this value is V of 0 by S, and then this value is 1 by CS, and this is current is I. Okay. So I multiplied by 1 by CS. That's what is happening here, and then this is just a voltage. So what I'm saying is, if a capacitor is given with some initial voltage, then you can replace the capacitor with this one when you are analyzing a circuit. Okay, I think with this we are ready to go and try some example problems. Okay, so I'll just go ahead. So anyway, we don't have to write it down and do that. So what problem shall we work on? Shall we look at what we tried to solve last time? We saw one example, so maybe I'll just start with that. The example was something like this. There was R1 C1 and then R2 C2. Okay, R1 C1, R2 C2, and this switch is closed at t equal to 0. Also, typically in the circuit diagrams of this kind of problems, you look at the arrow of this one. Sometimes the arrow is downwards. That means we are closing the switch at t equal to 0. Sometimes the arrow may be upwards. Okay, that means we are opening the switch at t equal to 0. So that also you notice in the circuit diagram. So the both can create transients. Okay, at the time of closing the switch or at the time of opening the switch. And then this is V. Okay, so this was our circuit, and we also had the values. Okay, V was 6 volts, and then R1 comma R2 both were 100 micro, sorry, 270 kilo ohms, and then C1 equal to C2 equal to 100 micro. Okay, so these were our parameters. We in fact connected the circuit and we noticed this thing. We have not taken exact time versus voltage kind of values, but we just looked at the behavior of this circuit. And what was noticed last time for this circuit? So we were mainly looking at VC2, and initially when I close the switch, both capacitors have 0 voltage at the beginning. So, and it will start charging, and then after a while there is a discharging path for C2. So in the steady state conditions, after a long time, C2 will discharge and the voltage will become 0. Whereas C1 cannot discharge, there is no discharging path, because this voltage will stop the current to discharge in this direction. So the maximum C1 can reach is equal to the V. If V was 6 volts, then the C1 will become 6 volts and stop there, and then the current will stop. So the point of what we noticed is this increases to some value and then it falls down. Okay? So that's what we'll try to mathematically show also. Okay? So from what we have discussed, let me just last time we were quickly doing it, but then let's revise it again. So if I transfer this into, this is in time domain, if I transfer into Laplace domain, we can get same circuit like this, V by S. So because it's a constant, it becomes divided by S, and then R1 remains R1, and this one I'll write it 1 by CS. So C1S, and this one is R2, and this is 1 by C2S. Okay. Now you can define I1 current in this loop, I2 current in this loop, and you will get 2 equations, and you can solve the 2 equations. But instead of using that mesh current analysis, I can use nodal voltage analysis, because I am interested, there is only one equation. So if this point is VB and this point is VA, so VA is already known because this is V by S. So one equation is right away solved. The second equation only we have to solve it. What is VB? Okay. So what is VB with respect to time, or what is VB of S? That's what you want to find it. Okay. And then once you get the answer, you have to transfer it back to some the answer will be in S domain. Then we have to go back to the time domain. So the way we do that inverse Laplace transform is just by looking at this table, trying to express the final result in either this form, or this form, or this one, and then finally we'll try to go back. Okay. So let's do this for this particular circuit. So I'll just work with these variables, and finally these values I'll substitute as I did last time. So KCL at B. So KCL at node B. There are 3 outgoing branches. So this one you can consider is as grounded. Okay. So what is the current in this branch? So current in this branch will be VB minus VA divided by the impedance of that branch, that is R1 plus 1 by C1S. Okay. Plus what is current in this branch? VB by R2 plus current in this branch VB by 1 by C2S. So because the other side is 0 volts, I can directly write it like that, and this is equal to 0. So this is Kirchhoff's current law at P, and from this, so VA is known, VB is unknown. Okay. So strictly speaking, I should be writing VA of S and VB of S and like this. Okay. So what is the next step? I can write VB of S equal to multiplied by this term, I can take that side. So 1 by R1 plus C1S plus 1 by R2 plus C2S equal to, this minus sign will become plus sign after going there, V of S, VA of S by R1 plus 1 by C1S. Okay. This one, no? Okay. Okay. So maybe I'll just slowly manipulate here itself so that you can see it. So this C1S I can bring it at the numerator. So multiply C1 by S and divide by C1 by S. So this will become 1 and this one will become S into C1 R1. Okay. So this part is done. Now the same thing I can do here also. See this VA of S I'll simply replace by 6 by S or V by S. Okay. So that because we already know that. So this is V by S. So this will become S and like this. Okay, that S gets multiplied in the denominator. Or should we keep it as it is? I think it will get cancelled. So I'll keep it as it is. Sorry for that. Yeah. Then I can bring C1S above. So then it will become V into C1. Then S into R1 into C1 into plus 1. Okay. So that I want these two to be equal. So when it goes there, it multiplies. So now maybe I'll write it here. So VB of S equal to VC1 divided by this one S R1C plus 1. Then I'll multiply the everything. So this whole thing will come here. Okay. C1S by S C1 R1 plus 1 plus 1 by R2 plus C2S. Okay. So these two will multiply. I'll get only C1 by S. Okay. So I'll write it VC1 C1S. Then this multiplied by this, I'll get S R1 C1 plus 1 by R2. Okay. And then this multiplied by this, I'll get S square R1 C1 C2. Okay. So now you can multiply numerator by R2. This is actually V into C1. So multiply by R2 and divide by R2. So here I'll get R2 here. This R2 will get cancelled. And then here I'll get one R2. Okay. Did I miss any other term? Which term? Oh. So there will be just C2S. And now I'll get R2 also there. Okay. Thank you for that. So now I'll just rewrite it like this. I will collect the S square terms and things like that. So V into C1 R2 divided by S square into so R1 C1 R2 C2 plus S into so R2 C1 R1 C1 R2 C2. So R2 C1 plus R1 C1 plus R2 C2. Okay. Plus 1. Okay. So this is what I wanted to get. This is directly VB of S. Now I can substitute the values. So because the values we have chosen 100 microfarads into 270 kilo. So the multiplication of any R and any C, because is 27 that you already saw many times. So kilo and 3 zeros is mega, and then mega and micro will cancel. 27 will remain. So if I substitute the values, then I'll get VB of S equal to numerator will be 6 into 27. So this V is 6, this term is 27. This one is 27 into 27, that is 729. So that is S square into 729 plus, so 27 plus 27 plus 27, so that is 81. So S into 81 and then plus 1. Okay. So I should write it 729 S square and then this is 8S, 81S. So was S in between 8 and 1? I don't remember, I removed it. So let me just now get rid of all this. See, now this is the kind of, I would think it's kind of a disadvantage of Laplace transform, although there are a lot of advantages. See, imagine solving this circuit using differential and integration kind of equations. That would be much more complicated. Here we are just algebraically we manipulated, multiplication, division only. But here it will be integration, differentiation. If you want to solve the problem in the time domain, it will be more difficult. Okay. Now the problem is, so what is 6 into 27? 162. Okay. Now the problem is, I am now stuck in the S domain. Finally, my objective, what is VB of t? But I have VB of S. I want to find VB of t, and the only transforms I have is like this. Okay. So that term I should express in one of these forms or the addition of these forms, so that I can write back in the time domain what it is. That is the problem. So what you should do here, so one thing you can do is, this is a quadratic equation, you find the roots of it. So then I can write it 162 divided by S plus alpha, S plus beta, something like this. So if I find the roots of this, I can write it like this. Okay, then I can write it A by S plus alpha plus B by S plus beta. Okay, so I can do partial fraction separation. Now this is in the form of this one. So therefore I can write it, because this is minus, it is becoming plus. If it is plus, here it will become minus. Okay, so I will get something like this: VB equal to some constant K1, e to the power of minus, let's say, what else shall we use? Alpha, beta is over. Let's say theta 1 into t. So I am just introducing new variables just to explain the concept, what is going to happen. So because it is S plus A, so I might get S plus theta, something like that. Oh, we already have alpha, sorry. It will be something like this. Some constant K1, in fact, unnecessarily, okay. So this is what we will get. From this term, I will get this part of the answer, then plus B into e to the power of minus beta t. Okay. So I will get this is my final answer. This is in the VB of t. Okay, like this. So this is what I am interested in to find out. What is A, what is alpha, what is B, what is beta. Okay. So now you have to find the roots of the equation and all these things. Okay. So maybe you can start doing it, but then at least from here there are some online tools that you can use to. In fact, you can solve the entire circuit using some online tool also. But then just to find the roots, I am using my laptop. Just give me a minute. So let me just write it down here. See, you will get alpha equal to something like this. Okay. Now I don't know whether 162 has been considered or not in this. Can someone confirm that? What are the roots of? So I think I have also considered 162 also in it. Let's do that. Minus 81 square minus 4 into 729 into 1 divided by 2 into 729. Okay. So are you getting the? This is what is the thing. So can you just quickly calculate it? What this one gives these two? Okay. Oh, so you already done this also, 0.22. Okay, so we have A and B values also. Okay, so thank you so much for that. So I'll write it down here. See, this is just a, see, because it is, the value is same, just the sign is different, I can take it common. So I'm taking common 0.22. Okay, wrong. So what is the value then? So for those who like to know what is the procedure, see, we solved up to here. Just now I have written down the roots of quadratic equation, found out alpha beta. Then what is the next step? In fact, I can take 162 common and then only worry about this 162 into A by so what is A and what is B, I have to find out in this. So if you substitute S equal to minus alpha, then this term will cancel, something like that, it will be there. Is it, so you are saying 2.7, but is it 2.6832? I'm just telling about the more decimals, that's all. So how much are you getting A? Minus 2 point? See, my answer is 2.68, your answer is 2.7, 2.683 something. 2.65, no. Anyway, see, it's 2.6, 2.68, let's go with it. So 1 will be plus, 1 will be minus, and then, so A is minus, okay. Okay, A is minus? You you stole my dialogue. Okay, see, the one, which one is bigger, that should be the minus sign. Anyway, it's good actually. So I'll write it. Okay, then I'll write the beta first. Okay, so e to the power of minus 0.01414 t plus e to the power of minus 0.09696. Okay, so sorry, minus. So here this 2.68, it is becoming minus A here, and 2.68 becoming plus B. So notice that this is beta, this is alpha. We can actually see this is simple function of time. Okay, so this is all in volts. Okay, so I can type this expression in a computer, substitute t equal to 0, t equal to 1, t equal to 2, t equal to 3 like that, and then I can always draw the graph of what is VB of t. Okay, so but then today we are not connected the computer to the projector and all. So we'll just quickly see, only take this term, okay, e to the power of minus 1.0141 t. So because this value is small compared to this value, so this will fall slowly. Okay, so that means so this is like, if I start with, see, t equal to 0, e to the power of 0 is 1, e to the power of 0 is 1, 1 minus 1 is 0. So t equal to 0, this whole term will be 0. So I'll start somewhere here, but only look at this term. Oh, forget about this term, only look at this term. T equal to 0, this is e to the power of 0 is 1, and then 2.68. So I'll start at 2.68. Okay, and then it will gradually fall. So this is the first term. Okay, like this. Now this is the second term with a minus sign. Forget about minus right now. E to the power of 0 is 1. Okay, so so it will also start with 2.68. Okay, so it will also start here, but then it will fall faster because of this one. But then eventually both will become close to 0. At the infinity they will meet. Okay, now introduce a minus sign now. Okay, the first term minus the second term, that is this gap. Okay, this gap is 0 initially, slowly the gap is increasing, and then the gap is decreasing again, and then finally the gap is becoming 0. So the result of that, you will find something like this. So, or maybe, so this is the pattern we saw last time in the previous, there is a video also you can see, that the voltage of this second capacitor gradually rises and then it reaches some maximum value and then it falls. Okay, did someone remember how much was the maximum value here when we did that experiment in the class, in this one? 1 point? Yeah, so it was about 1.58 volts. Okay, 584 or something like that we got it. Starting from 0, I touched that value and then again started falling down. Okay, and if we repeat that experiment once again, I can also find out at what time it is touching the maximum value. Okay, what? 23.2 seconds. So I'm not sure about this, but see, now I have this expression, I can always find out what is the maximum value of this. So how do you want to see? I want VB max. How do you find that? Differentiate and equal to 0. And if there is exponential term, it's very easy to differentiate. So what is the differentiation of this? What is VB dash of t? So 2.68. So differentiation of this. So minus of this, minus 0.01414 e to the power of same thing, minus 0.01414 t, and so this is minus and the same thing. So 0.0, so this will become plus 0.9696 e to the power of minus same thing again. So can you just help me with the next step now? What is this into this? Yeah, so this we have to equate to 0. So this term will get cancelled because we are equating it to 0. This term will get cancelled, and then this is minus sign, this is plus sign, and there is 0 on the other side. So I can remove all that and then put equal to here. Okay. Then you divide these two. So maybe this term I'll take it there. So what is that? 0.01414, isn't it? 4114. So what is this ratio? Okay, 6.857. Now how do you find T? So apply log on both sides. Okay. So this one I can take it up. Is it so? If you apply log, what happens? E will go. Here what happens? Log of this plus the other term, right? So I'll get apply ln both sides. Okay. So this side I'll get minus 0.01414. Okay. T equal to natural logarithm of 6.857 plus, or because of this there is minus, I hope I am doing it all correctly. Okay. Now what you do, this is minus, that is minus, so maybe you can just solve this. So this is also just known. So can you just quickly do that? What? Okay. This dialogue you should not have said. So, okay, what is T? Anyway, you don't have mic, so it's not recorded, so fine. So what is T in this? So after solving this, so this is a constant, this you can bring it this side and then do the subtraction, divide and everything, you will get what? See, maybe what we can do is we can just look at the other video, and then on the video there is time coming at this one, so we can, using that time, we'll see whether the maximum was reached in 23.2 seconds in the last video. So you can check that. Now if I substitute this back into this, will I get 1.58? If I substitute this 23.2 here and here, and then solve this whole thing, will I get the maximum value 1.584? Yes? Where is your calculator? He is just saying yes. It's okay. So you check that, and if it is not coming, then send me an email. So see, these things are all like you might have learned the theory a lot of time, but practically you can actually cross check. That was my intention, to do that circuit in the classroom and then try to see that these are all not just the mathematical manipulations. Physically also you can verify that yes, really it is, so many things you are verifying, like differentiating equal to 0, will it really go to maximum value, all this kind of stuff. Okay, so let's do some more circuits, one more example, then we'll go forward. This is not what? Okay, thank you. So we got the answer 1.65. VB at T equal to 23.2, right? Is equal to 1.65. But this is our calculation, 1.65 volts, and our experiment is 1.58. Okay, so more or less matching, and the difference is because of the parameters. Okay. Okay, so I'll just give one more circuit, and then I also want to introduce another idea through that. Okay, the circuit is like this. So this is just connected. So here plus minus V of t. and this is I of t. So this is 2 farads, 3 ohms, 1 ohm and 4 henries. Okay. So practically this is very difficult to create because 2 farads is very high value, 4 henries is also very high value. So normally you will not see this kind of circuit, but then for analysis we can do it. So this is in time domain. So if I convert to Laplace domain, what happens? Okay. Before doing that, is there anything statement given about the initial conditions? What initially what is the charge? If that is not given, you can also find out. Okay. So here supposed to be a switch here. Oh, I think that is the whole point about this problem. One second. I am trying to figure out whether the switch is being closed or switch is being opened, which is more interesting. So before the time t equal to 0, if the switch was closed and then you open the switch, then it is interesting. Okay. So I'll put the arrow upwards and then say t equal to 0. So what it means? At t equal to 0, I am opening the switch. Okay. Is that interesting or? No, I think we have opening another problem. Maybe I'll just do this one. Okay. The next problem will be opening of switch. So, okay, now look at this. At t equal to 0, I am closing the switch. Okay. The question is, what is I of t? So at t equal, so that I want an expression at any value of t, and v of t may be a DC voltage. So let's say V volts, or let's say 10 volts or something like that. Okay. I apply 10 volts DC, close the switch, how it will react. Can you just get the intuitive feel? What is the initial current? I'll apply 12 volts. 12 volts. Immediately I close the switch, how much current will be there? 3 amperes. So most of you are saying 3 amperes. That is because this will act as open circuit, this will act as short circuit. I close the switch, then the only path is this one, or this is a short circuit, right? Oh, this is open. So 4 ohms resistance and 12 volts, so current is 3 amperes. So initial conditions, I of 0 is 3 amperes. Just immediately after closing the switch. What about the capacitor voltage? Because it has to be given actually. See, I can always charge a capacitor and then connect the circuit. So let's consider it as given data. V of 0 is 0. Okay. So now we are ready to go to Laplace domain. So just I am just changing it now. So this is 12 by S. This is 1 by 2 C. Okay. 2 farads into 1 by 2 S. Okay, and this one is 1 ohm, this is 4S. Okay, and then this is 3 ohms. Okay. Now, what is the total impedance? So the current is I of S and the voltage is V of S. Okay. So voltage and current, it's like the total impedance of this. So what is the total impedance? So I'll say Z equal to, okay, Z of, I can also write Z as a function of, so this is impedance in the Laplace domain. It is like 1 by 2S is in series with 1 parallel with 4S, which is also in series with 3. This is the circuit, right? Just like this one. Now, so I can write it now, 1 by 2S plus 1 into 4S is 4S divided by 1 plus 4S. Okay, this is parallel circuit. So Z1, Z2 divided by Z1 plus Z2 plus 3. Okay. Now I can further simplify 2S multiplied by 1 plus 4S, and this one will be 1 plus 4S, and this one will be this into this. So 8S square. 8S square. This is plus, right? plus, so this into all of this, okay. So 6s, then this into this. So 8s square into 3, 24s square, okay. So I'm getting like this. So this is again, I can further simplify. So 8 plus 24, 32s square, plus 4 plus 6, 10s, plus 1. Is it so? That's all. So 1 divided by this, I'll keep it 2s, 1 plus 4s. Okay. So this is my impedance Z of s. Okay. What is this impedance doing? I'm just my Ohm's law will still apply. So V of s equal to Z of s into I of s. Okay. So this whole term will come here. Okay. So I of s is nothing but 1 by this. Okay. So I can write it, if I want to know what is my current, then I'll just reverse this. So this is 2s, 1 plus 4s divided by 32s square plus 16s plus 1. I hope it's all correct. Okay. Now I can substitute what is Vs. What is V of s? It is 12 by s, because DC voltage 12. Okay. Oh, this is 10. Okay. So now I can, I have this circuit, so I can now solve it. I think this S will get cancelled, is that correct? So 2 into this one is 24 plus 24 into 1 plus 4s divided by this one, 32s square plus 10s plus 1. Okay. So this is I of s. So again the same problem, I want what is I of t. Okay. But this is in a different form, so I have to write it in terms of this one, so that I can get what is I of t. Okay. So how do you do the partial fraction for this? Again there is a quadratic equation. This will be alpha beta, so s plus alpha, s plus beta roots, and then you separate it out, find out what is a, b, and then you can do it. Okay. So maybe I'll once again use my laptop to just find the partial fraction of this, and then we'll see. What? Doesn't have roots? It's creating imaginary roots. That's okay, not a problem. That might be a problem because of two reasons. One is, see, the circuit itself may be such that it is creating imaginary roots, or my calculations may be wrong and then I am getting imaginary. Both are okay. Okay, but then for this example I did not want to have imaginary roots, so somewhere I made a mistake. Let's quickly look at that. So 1 by 2s is okay, 1 4s parallel is okay, 3 is okay. This is also okay. So this is correct. This is correct. Then what happens here? 2s into 1 plus 4s. So this is by 1. So 1 plus 4s plus 8s square plus 6s is correct. And then 4 to 8, 3 is 24. S square is also correct. Okay. And then okay. I think here I made a mistake. Because this 1 plus 4s is there, s cannot be cancelled. But what about this 1 plus 4s? Okay. Then Where else is the problem then?
So in S domain, so why does it matter if you have complex? Probably we should not get complex roots in time domain.
Yes, your point is correct. We don't worry, but then when I solved that house at my home, I did not get complex roots, so that's why I'm worried. Let me just, I did not write everything. Uh, 8s square plus 2s. Can you just check if I made any mistake once again? Otherwise, we'll go with it. Let there be complex roots. I'll just write the answer with that. See, if we can't find any mistake in this, then we'll go. Maybe I made a mistake earlier. So, what are the roots? One second. Okay, so actually I lost my Wi-Fi connection, so I am not able to solve the partial fractions of this. So we'll just come back to this. We'll quickly look at another problem, and then towards the end, or maybe we'll resolve it, and then I'll send you the answer in some form. Okay. Let's look at another question. For the time being, I'll just keep this as it is. The question is like this. We don't need this now. So here it is opening of switch, t equal to 0. And then there is a voltage source here. It says 60 volts. This is and there is a capacitor here. Okay, so why I found this circuit interesting was that the calculation of initial conditions itself, like you can give half marks for that only. So the calculation of initial conditions itself is quite interesting in this circuit. Okay, so that's what I am now asking you to do. This is a 60 volts. Before t equal to 0, the switch was closed. At t equal to 0, the switch is open. Okay, so I am asking you what are the initial conditions, which means what was the voltage of this one and what is the current in this circuit before opening the switch. Okay. So can someone quickly or so I'll just, for the time being, I'll close the switch. So how do you go about, this is a DC voltage, how do you go about calculating the initial conditions in this? So you don't have to write down many equations, you just observe the circuit, you can get some ideas from that. So now let's say the switch was closed for a very long time, okay, and it's a DC circuit with a DC voltage source, okay. So for all practical purposes the inductor will be a short circuit and the capacitor will be open circuit. It will charge to certain voltage and it will stop there, okay. So if this is open, so I can just disconnect this, and this is short, I can just short circuit this, okay. So then I have a DC circuit, simple DC circuit. So what is a DC circuit? The current is going like this. This is one path, 10 kilo ohms. This is another path, 10 kilo ohms. So 10 in parallel with 10. So you will get 5. Okay. So 4 kilo ohms plus 5 kilo ohms plus 3 kilo ohms. So 4 plus 5, 9, 9 plus 3 is 12 kilo ohms. Okay. And this is now this side it is open. So this side also it is open. So 12 kilo ohms divided by 60 volts. So 60 by 12, 5 milliamperes. Okay. So 5 milliamperes is flowing like this. Then the question is how much will go left and how much will go right. So because this is 10K and this is 10K, it will divide half. Okay. So this is 2.5 milli, 2.5 milli. Okay. Now if 2.5 milli is going this way, how much is the voltage drop in this? So 5 kilovolts into 2.5 milliamperes. Okay. 5 into 2.5, how much is that? Yeah. So 12.5 volts. Okay. So which side is high voltage, which side is low voltage? So because the current is going like this side is high voltage, this side is low voltage. Okay. Now what is the voltage drop in this 4K? 4K into 5 milli. 4 into 5 is 20. Kilo and milli will cancel out each other. So this is 20 volts. Which side is high voltage? This side is high, this side is low. Okay. So I start from here. I want to find out what is the voltage of this point with respect to the voltage of this point. So I start from here. My voltage increasing by 60. Okay, so plus 60. Because I am starting from here, going from minus side to plus side. Then from here to here, voltage is decreasing by 20 volts because I am losing the voltage in the drop. So minus 20. Then from here I am coming this side, I am again losing 12.5 volts. So minus 12.5. So what am I remaining with? 60 minus 37.5, 32.5. So how much is that? 27.5. So the voltage of this point is 27.5 with respect to the voltage of this point. Therefore, the capacitor will charge up to 27.5 volts and then the capacitor will, current will be 0 and then it will wait there. Okay. So therefore, VC of 0 is 27.5 volts. Okay. Before opening the switch, okay, some charge has been already, some voltage is stored in this voltage source. And the 5 milliamperes divides and then again combines here. The same 5 milliamperes will come here, and therefore IL of 0 is 5 milliamperes before closing of the switch. So some current is there here. So which is in this direction, and the voltage is in this direction. Okay. Now after establishing what are the, see, if you have 3 inductors, then there will be 3 initial currents. If there are 10 capacitors, there will be 10 initial voltages. So all of those you have to calculate before starting the. So now you can go from here to S domain. Okay. So what do we get? Now I can actually simplify. What way we can simplify this? See, when I open the switch, in the S domain, I'll open the switch. Okay. So first of all, the question is what am I interested in? Final output. Okay. Let's say I'm interested in knowing what is the voltage across this inductor. Okay. So let's call it VL of T. So this is my final output required. Okay. So if I want to only know about this, then I can rest of the circuit I can actually simplify. Okay. So what way we can simplify? See, when I open the switch, this branch totally gets disconnected. Okay. So I can totally remove this branch. Then this will become two resistances in parallel. So 5K in parallel with 15K. Okay. So what is that? 5K in parallel with 15K. So 5 into 15 by 5 plus 15. So 5 fours, and then this is how much? 3.75 kilo ohms. Okay. So this whole thing will become one resistance, and this is 3 kilo ohms. So totally 6.75 kilo ohms. So I'll get a final circuit something like this. This is capacitor 100 microfarads with a voltage of 27.5 volts, and then this is resistance, which is 6.75 kilo ohms, and then this is inductance, which is 200 millihenries with already current flowing how much? 5 milliamperes, the initial current. Okay, and this is the initial voltage. Okay. So but this is still in time domain. So what you can do now? So this one, if you convert to S domain, so this is where again the interesting point comes. Okay. So we are interested in voltage of the 200 millihenries. Okay. So I want to find what is this voltage. So what I can do, so this is 1 by CS. Okay. So 1 by 100 micro into S. This R will remain same, 6.75 kilo. Now here I will have to also put a voltage, this one. So this is 27.5 by S. Okay. So remember the initially just beginning of this lecture we have drawn some how the capacitor will look like in the S domain. Okay. If there is some initial charge, then it will come like this. Okay. So 27.5 was the initial charge, so by S. Okay. Maybe quickly I will review that. So if you have a capacitor, so this is I of t, V of t, then what is that? I of t is C into V dash t. So I of S is C into V of S, S V of S minus V of 0. Okay, so this is what we are doing. So this, if I want to know what is the total voltage, so this is total voltage, then I have to write it in terms of, now we have to lose this, V of S is equal to 1 by C I of S, then minus plus V of 0 divided by S. Okay, just I reorganized it. So this is exactly what we are drawing here. Okay. So if there is a current is flowing I of S, so this I of S multiplied by this is the first term, this is some voltage, and this itself is the other voltage, V0 by S is the other voltage. These two voltages together will add up to my initial voltage of the capacitor. Okay. So the same thing happens here, inductor, and then I can put a voltage source. Okay. Or if I am interested, I can actually put a parallel current source also to find this thing. We will go with the voltage source. So this is 200, that means S into 200 milli. So or I will write it 0.2 S. Okay, S into L. We still have some time. So this is plus minus, okay, or is it? So because the current was going down, it will try to continue that same direction of current. Therefore, the voltage induced will be something like this. That's another quick way of defining what way the voltage will be. And what will be this voltage? This will be, is it like this? I0 into L. Remember there was one term L into I0. Okay. So L was 0.2 and I0 is 5 milli. Okay. Is it, so 5 milli into 0.2. This is almost, so this is 1 millivolt. Almost negligible, but anyway. So 1 millivolt. But it will be in downwards direction. Will it have by S also? Into S? I'll have to redo it. So this is L and this is I of t, this is V of t, then I'll write V of t equal to L into I of t, then V of S equal to L into S, I of S minus I of 0. Then I of, so I think I can stop here itself. So total voltage is, yeah, there won't be any this thing. I don't have to put any S there. So Ls into I of S minus L into I of 0. Okay. So notice that the sign of these two is different. So I'll have, the current is flowing like this is high and this is low. So the sign of these two is opposite, so that's why there is minus sign there. So I think we are all correct. Okay. Now what is the unknown in this? I can find what is Is, and then I can later on find what is the total voltage, because we wanted to know this voltage. Okay. So how do you find Is? So everything else is known. It's like just Ohm's law only. So I can write one equation maybe here. Okay, so I'll write simple Kirchhoff's voltage law. So from here to here, 27.5 by S. Okay, and then there is a drop. So minus Is by, actually it will be 1 by, no, Is into, so it will be by 100 micro into S. Okay, then minus, so Is I can take it common, 1 by 100 micro into S plus 6750 plus 0.2 S. Okay, and then minus 1 milli. I'll just ignore this because it's just 1 milli, I can ignore it. So equal to 0. So now I can find what is Is just by transferring to the other side. So 100 micro is how much? So 10 power 6 by, so this is 10 power 4 by S. Okay, so this equal to 0 I can remove, make it this one equal to. Okay, and then I can bring this S this side, then this S will cancel, here S will come, here S square will come. Okay. So now Is is 27.5 by 0.2 S square plus 6750 S plus 10,000. Do we still have again the same problem of complex roots? So again we have to do the what you call partial fractions. Let me see if I